Welcome back to Mechanical Engineering Made Simple.
Today, we are tackling the essential design questions every single engineer runs into when working with gears. We're going to follow the entire life cycle of a gear system. We'll start at the very beginning with the blueprint, sizing, stress, and strength. Then we'll get into the dynamics of how it actually operates. After that, we'll zoom out and see how it fits into the bigger system. And finally, we'll play detective and get into failure analysis. All right, let's dive in.
So first things first, we're starting with the most fundamental challenge there is, figuring out the right size, strength, and material for the job.
This is probably one of the first questions you'll ask, and it is absolutely critical to get it right. Luckily, engineers have a really powerful tool to get started, the Lewis equation. Now, this equation might look a little intimidating, but it's actually telling a pretty simple story. It's all about balance. It helps us find W, which is the maximum load a single gear tooth can handle. And that load depends on a few key things. S is your material strength, and F is the face width of the gear. But the really interesting part, I think, is Y, the tooth form factor. This means the shape of the tooth is critical. A better designed shape can take way more stress because it spreads the load out evenly. Then, of course, you have to factor in the gear's size and speed. It really is the essential blueprint for a gear's strength. Okay, so you know the stresses, but what do you make the gear out of? The material choice has a huge impact on strength and durability, and it's almost always a trade-off between hardness and resistance to shock. And as you can see here, the application really drives the decision. Your standard carbon steels are great workhorses for general-purpose stuff, but if you're building something critical, think aircraft components, you're going to need high-end alloy steels that can be hardened to incredible levels. A Rockwell C of 58 is seriously tough. But then, on the flip side, for a high-speed, low-load application where noise is your biggest enemy, you might go with a non-metallic material. It's all about picking the right tool for the right job. And this is such a great point for Magma. It explains exactly why standards are so important. They give you a safe, conservative baseline to work from, a built-in safety factor. But it also hints that there's more strength to be had if you're willing to do a more detailed, specific analysis for your exact application. You can often push beyond that one-size-fits-all approach. All right, let's move on. We're going from the static design on a piece of paper to the real world of a running machine. And as soon as things start moving, a whole new set of problems appear, namely dynamics like noise and vibration. We've all been there. The gearbox is screaming, but only at a certain RPM. Well, that noise is usually just a symptom of a much deeper issue, torsional vibration. And that vibration can come from a few different places.
Look, some noise is just going to happen. The standards often suggest that anything under 85 decibels is pretty normal. But if you're getting excessive noise, that's a huge red flag. It could be pointing to a manufacturing problem like sloppy tooth finishing, or something much, much worse, like you're running dangerously close to a resonant frequency.
And this is the one phenomenon you absolutely want to stay away from. Hitting a resonance frequency is like pushing someone on a swing at exactly the right moment every single time. The swings get higher and higher until the whole thing breaks. In a gearbox, that means catastrophic, destructive failure.
But here's the good news. You can actually engineer your way out of resonance. It's not just some random bad luck. It's physics, and we can control it. By doing things like strategically changing the stiffness of a shaft, or maybe moving a heavy component, or even adding a dedicated damper, you can shift that natural frequency away from your operating speed and keep the entire system safe.
Okay, let's talk about the bigger picture. Because a gear never ever works in isolation. Its performance is deeply connected to the entire system it lives in. Things like alignment, lubrication, and heat. If your gearbox is getting hot, it's a direct sign of energy loss. Every single degree of extra heat is just wasted power, and it's being generated by friction and fluid dynamics. So you have to ask yourself, where is all this heat coming from? Is it from the gears just sloshing through the oil bath? We call that churning loss. Or is the heat actually coming from the friction right at the gear mesh itself? Figuring out the source is absolutely the first step to managing that heat and making your system more efficient. Oh man, this is a big one. The short answer? They are extremely sensitive. Even a tiny bit of misalignment can introduce forces and stresses that the system was never, ever designed to handle. And here's why that is so important. Those alternating stresses from things being out of line, they start a ticking clock. Even if you have a flexible coupling that's absorbing some of that stress, it will eventually lead to fatigue failure. It's just a matter of time. Perfect alignment isn't just a nice to have. It is absolutely fundamental to the lifespan of your design.
And that brings us to our final section. Let's look at how gears are actually made and, inevitably, why they break. We're going to connect the dots between manufacturing choices and how they perform or fail in the real world.
The quality grade you need isn't just some number you pull out of a hat. It's dictated entirely by what your application demands in terms of noise and strength. And those things are a direct result of how the gear was manufactured.
So choosing between a process like hobbing versus a more expensive finishing step like grinding, that's a classic engineering trade-off, right? It's a balance between cost and precision. But for those really high-speed or low-noise applications, that extra grinding step is what buys you the accuracy you need to prevent the dynamic loads that cause all that noise and vibration in the first place.
Okay, so the worst has happened. A gear failed. Well, that broken tooth tells the story. We have to be forensic engineers here. Was it a single, massive, catastrophic event? Or was this a slow, creeping death that happened over millions of cycles?
What's really crucial to get is that sometimes one failure mode can actually lead to another. The research shows that something like gradual wear, say micropitting on the tooth surface, can create stress risers that eventually kick off a classic bending fatigue failure. So what started as a simple surface issue ended up with a completely snapped tooth. It's a domino effect.
And there we have it. We've gone through the whole life cycle, right from that initial calculation on paper with the Lewis equation all the way to the final fracture analysis of the actual hardware.
That's it for today, Design Junkies. If you're getting something out of this, follow the podcast, leave a review, and don't forget to check out our YouTube. It helps the whole family grow, learn, and build better together. A family that solves together, stays together.